Hello and welcome to Retro Circuits. If you're new to this channel, I talk about retro computers, how to tinker with them, hack with them, program them, and also about retro video games. Today's episode, we're going to analyze line by line a simple program in basic programming language that draws dots on the screen. This is by using the screen RAM that we discussed in the part 3 of this programming series. Let's get into it.
This is what the program does. Run it, and we have this cursor that we move with the arrow keys. And then when we press space, it will draw a little dot. If we go back to the same place there is a dot and we press space again, it will delete it. So it's very, very simple. And we will see the source code and how I analyze it and see how it works. Let's start line by line to understand this program. First of all, for the Commodore 64 in BASIC, you have to number the lines yourself one by one. So in this case, most people used to just number the lines in 10 by 10, like 10, 20, 30, 40. The reason for this is because maybe you decide later, you realize later that you need to add one more line, so you have space to do it. For example, here we can see that between line 60 and 70, there is another line here, 65, and the reason for that is that I decided later to add a line in between to add that. So this is important that you keep that in mind. It is a little bit tedious that you have to add the number of lines yourself, but that's how it was at the time. Nowadays, if you any modern programming language, fortunately, you don't have to do that. Another important thing here is that everything that you see is in lowercase. On the Commodore 64, there is really not lowercase and uppercase. So everything that you see here, when you copy and paste into the simulator, in device emulator, it will become automatically uppercase. The reason here is lowercase is because sometimes when you have this code in uppercase and then you copy paste it into the simulator, it gets converted into some characters that are not recognizable, or it becomes the equivalent of pressing shift in the Commodore 64, and that characters will give you a symbol, a graphical symbol in the pesky table. So it's important that when you do this copy paste, you keep everything in lowercase, and then it will be automatically converted in uppercase. So that's why we see this here in lowercase. The first line, number 10, is a comment. Comments start with the command rem. So everything after rem here is a comment. The interpreter in BASIC is going to ignore everything we write there. So basically the interpreter will go line by line, reading each command and executing them. So the first one it's going to find is a rem. So I say, okay, after the rem, I don't do anything with it. It just skip and go to the next line. So this is useful to comment your code. So another programmer, another person that sees the code, you will understand what it does. And also for yourself, because in the future, you might forget why you make a certain decision, why you wrote a certain piece of code in a specific way, and that comment can help. The second line, 920, is print CHR $147. Well, CHR dollar is a string function, which is called, meaning that here we put a number. This number here is going to come from the PETSCI table, which is basically a table where you have a number and a character, a number and a character. So for example, number A corresponds to the character 65. Well, if you put, for example, CHR $65, it will pick up that from the table and it will print the letter A on the screen. There are many codes in the PETSCI table which are not printable. For example, the 147 that we have here basically prints reverse heart symbol. What it does is it clears the screen on the Commodore 64. So that is not really a command that a character that we can use to write anything useful in particular, but it has that particular function. There are others, like for example tab, return, and all these kind of other characters which you cannot really print. So the PETSCI table it has all of them. If you're not familiar with the concept of a function, basically all these converts when you put here like 147, or let's say, for example, we put here 65 for the letter A. It means that all this content here, the function, when it returns, will return the letter A. So it's a string function, meaning that when it executes, it will return a string, a character, in this case A or whatever. So remember that the concept of a function, you always will pass a parameter to the function, and then the function will compute internally something and it will return something to you. You have to think about it in the mindset of, okay, well, this part here is going to, the whole thing return something is going to be replaced somehow in something that it returns. In this case, for example, instead of 147, if it was 65, the whole thing will be replaced by the letter A. The reason I'm also doing this is to keep the compatibility with the emulator, because in a Commodore 64 you can also accomplish the same by pressing Shift plus the Control Home key, which is something that you don't have on a modern PC. So in this way, I try to keep you completely independent of having a real Commodore 64. The line number 30 uses the command poke. What is the command poke? Well, imagine the Commodore 64 memory, like if you have a lot of cells, one after the other. So each of these cells have an address, a memory address. And each of these cells can accomplish a certain purpose. For example, in the screen memory of the Commodore 64, you have this area of the screen, which is I explained in the previous video. Here, the first cell, the first location, corresponds to the address 1024. And the last one here corresponds to the address 2023. So basically, you have 1000 bytes in this area. And this is the address of the first one. So what happens here is that every location in memory has an address. So the command poke, what it does, you say, okay, poke, for example, 1024, go to the location memory number 1024 and, add the parameter, for example, 1. So in that cell, somewhere in the Commodore RAM, if this is the location, for example, 1024, it will add the number 1 in there. It will set that number in that memory location. This allows you to create all sorts of manipulation, because the computer is checking on certain memory locations for accomplish certain purposes. For example, in case of 1024, is the memory location corresponding to this area of the screen with this cell of the screen. If you modify that, of course, that area will show immediately the effect of that modification. So this area here, for example, the background color of that area is controlled by the memory location in 53281. It means that the computer operating system is checking on that particular location there, and based on the value of that location, it will set the color. The number 0 corresponds to the color black, the number 1 corresponds to the color white, and so forth, until we get to the 16 colors of the Commodore 64. So in this particular program, I wanted to make this part of the screen black. So poke 53281, which is the memory location of that particular area which controls the color, and 0. Basically, this automatically makes that area of the screen of a black color background. The next line is another comment. Here I say init variables. Basically, in this area, I'm initializing a series of variables. So what is a variable? Well, remember when we were talking about the memory on the Commodore 64, and you imagine this as a series of cells, which each of them contain a value? Well, each of these memory locations have a number. So in order to make it easier for us to make a reference to a particular location in memory, what we do is create a variable. In this case, for example, the variable SM has the value 1024. Well, automatically, the basic interpreter, what it's going to do is going to pick up a particular location in the RAM. We don't know exactly which one. And will assign to this label, this identifier, that particular memory location here. So every time we write in the program SM, it will know that that SM corresponds to this particular location in the RAM. In this case, we said to put the number 1024. I know now you might think, okay, well, wait, each cell in the memory is supposed to be 1 byte, and 1 byte can have a number from 0 to 255. So how do you put a number bigger? Well, in that case, you take more than one location to split that number there. But this is a process that is done internally by the basic interpreter. It's something you don't really have to worry about. The important thing here to understand is that you can assign a value to an identifier, to a variable name, and then you can use that later in the program. So if you need to make a modification, you don't have to go through each piece of the program to modify a number. What you do is just you assign the variable, and then if you need to change that in the future, you just change the value whenever you define it initially or anywhere that you modify it. And that will allow to everywhere else where that value is used to be automatically changed for you. Another important thing here is that we see this column. Well, what it does is to put more than one command in the same line. We could do, like, for example, 50 SM equal to 1024, and then we could do 60, and then that would be CM equal 55296, 70 MPV equal 0, and so forth. But because we are here initializing a series of variables, in this case, it's easier to just put all of them in one line. Also to somehow get it in a bit more like neat and easy to see way. So here what we are doing is defining this variable, assigning this variable, assign this number to this variable, to then assign 0 to this, 32 to this, and 0 to X. We will see later what's the purpose of all of them. Then line 16, we have another poke command. SM is 1024. So this is poke 1024 plus X. X is 0 plus 0, comma 224. This is the same as saying poke 1024, comma 224, where 224 is in the screen codes corresponds to this full rectangle here. And this will be the cursor that we will move around the screen to see, to place all the circles that we want to draw the image that we want. As a way to initialize the system, I wanted to put this on the upper left corner of the screen. Why do I have to put this plus X, which initially is 0? Anyway, so wouldn't it be easier to just write this and get away with it? Well, there is a reason not to do that. And the reason is because, first of all, we are using a variable here, SM, to identify this particular memory location. Imagine that in the future I want to move the memory location of that area of the screen, because we can do that, and also we can move that the initial point of that screen memory somewhere else. So I don't have to change everywhere where there is a 1024. I can just change the value SM. Another reason for putting the X here is because what if I don't want the cursor to be here, for example? What if I change my mind later and I want to put this somewhere else? I want the program to start with the cursor here, for example. Well, to do that, I don't have to recalculate here anything. The only thing I have to do is when I initialize this X value, I just put enough offset. I add their number that I need to actually travel all the way up to this point. So you want to be a little bit careful here because, premature optimization is the root of all evil, as a very important computer scientist, Donald Irving Knapp, I hope I pronounce him properly, he said basically what it means is that, it's good that you predict a little bit what you might need in the future. So you have to design your software in a way that, okay, maybe I want to do this change, maybe I want to keep this kind of flexibility or so forth, but don't do too much, because sometimes you might spend a lot of time in a potential future feature that you might never need, and then you might spend a lot of time and resources in doing that. So this is a little bit of thinking ahead in the future and say, okay, maybe I want to put this cursor here, and I'm doing in this way to just easy that potential situation. And so in the future, I only have to change this value here and I'm done. I don't have to refactor a lot of the code. And the last in that line is poke CM, which corresponds to the color memory. It will be 55296 plus 0 in this case, because X is 0, 1. So this is the same idea. The only difference is that this is for the color memory. So in that screen where we have before that here we start at 1024, at the same time in that same location we have 55296, which is another memory location that matches the color we want to put in there. So we can control the color of each cell individually. In this case, I wanted that cursor to be white, so black background, the white characters is going to give more contrast. Line 70. Here we have a new command, the command get. This command basically reads a character from the keyboard cache and put that into a variable. So every time you type a key, there is a little buffer, so cache for the keyboard, and it keeps those characters. There is a limit for that. I think it was 10 characters if I'm right. So the point is that get is reading every time that you type a key and will put that into a variable, in this case a $. Then the next command is if. In the same line, you see the column is to put two commands in the same line. So the next command is if. This is to comparison. It checks if something has a particular value. In this case, for example, it's checking, okay, if the $, which is going to have in the character that we type on the keyboard, if is equal to nothing, then go to 70, and 70 is the line where we are. So in basic, we make a huge amount of use of the command go to, and it could be very dangerous because with go to it's difficult to trace back where things are coming from or where things are going. So for example, in this case, I'm making a go to the line number 70. Let's say that I change this line by 71, 75 or something when I refactor in the code. So I need to be careful because you have to keep an eye on here. Otherwise, when go to reaches, the interpreter reaches to this command, it will go to line 70, but maybe 70 is not what I had initially. So you have to be careful when using go to. So basically what it does here, it says, okay, read the keyboard, put whenever it's in the keyboard in this variable, then check if this variable is equal to nothing, it's empty, then come back and do this again. Keep reading the keyboard, check, is the variable has something? No. Okay, get back, read the keyboard again, and in this loop, constant loop, checking if it's or it's not. Then if you type a key and you press a key, it means that, okay, is $, this variable that keeps the character that you just type, that you pressed on the keyboard, is it empty? No, it's not empty. I press, for example, the key A. Okay, so this condition here is false. Then it's not going to execute the go to command either, so it's going to move forward to the next line, which is going to be the line 80. And that's basically the mechanics that is used here. So it's all the time listening to whenever you are pressing any key you are pressing on the keyboard, reading it, checking. Is it something? No. Okay, I keep reading. Is it something? Yes. Okay, move to the next line and do something. And that's the moment you just operate and you just process that input. The next line is the number 80. Well, here is where we basically will process all our input from line 80 to line 130. And then you can see here we go back to line 70 here to check and read the keyboard again. So what we are doing is checking a series of characters that we are pressing on the keyboard and take an action. So here we have if, then ASC $, equal to 29, then increment the value of the variable of and jump into line 1000. What this means is, first of all, if right? If whenever something, it will return true or false. Then based on that, if it's true, then do something. If it's false, nothing, and just continue. So in this case, we have if, and the ASC, and then the variable. The ASC is a keyword, and it takes the first character of a string. Okay, you can pass one character. In this case, we're passing only one when we type, but you can also pass it as a string that will be contained in this string variable. And what it's going to do is going to map that first character to the Commodore ASCII table, which is called the pesky one. So we will know which number of that pesky table corresponds to the character that we typed. So what I'm doing here is checking the first one, if it's the number 29. The number 29 corresponds to the right arrow key. And these are all the numbers that correspond to the other arrow keys. So for example, the left arrow key corresponds to the number 157. The up arrow key corresponds to the number 145. Down corresponds to the number 17. And as we saw before, right corresponds to the number 29. So here we mapped the arrow keys of the keyboard, and we can use them to identify where we are moving to move the cursor around the screen as we want. Then we have this variable here, off, equal to x plus 1. This variable of the name suggests that it is an offset. So what I want to do is, okay, when number 29 that corresponds to the right arrow key is pressed, what I want is to add one position to the current one. Whenever I want to add one step. So in the screen, when you have your character here, when you start, this is 1024. I want that when I press the right arrow key, it will add 1. So it will become 1025, which is the next position. So that's what I want to do. I want to move into that position. And all this area here, what it does is basically changing that offset and say, okay, if you move to the right here, you add 1. If you move to the left, you remove 1. And what happens if you move up and down here? Well, what it's going to do is adding 40, because remember, you have 40 columns in this screen and 25 rows. So if I'm in this position, what I need to do is add 40 steps, 40 positions. So it will add from here, we'll move all the way to just the same position but one row below. And in the other case, we just subtract, we take out the 40 positions, so it will move all the way back to the left and then go up to the one on the top. Then we have column. Another command is gosub 1000. Well, what is gosub? Gosub, I don't know exactly how that would be pronounced. The important thing is that this is very similar to goto. The difference is that goto, for example, if I go to line 20, okay, it will go there and that's it. And that will continue the execution of the program from the line 20. But what gosub does is something similar to a function that returns something. So for example, if I say go to line 1000, it will go to the line 1000, execute whenever it's there, and continue the execution to whenever other line exists in that until it finds a line that says return. When finds this command return, it will return just after the next line of the gosub call. So for example, here we have a gosub 1000. What it's going to do is going to jump here to the line 1000, and it will check this condition. If it's true, it will execute return, and return will return this here just to the next line. In case this condition is not satisfied, then it's going to check for the next one. So it's going to go to the next line, it's going to check this condition. If it's satisfied, it's going to return to the next line. If it's not, it will continue so forth until it hits a return. In this case, the return is going to return here again to the next line 990. So that's basically what gosub does. So it's very similar to calling a function. It's used for that purpose. Even if you cannot really pass a parameter in that call, like in other programming languages, what you do is basically jump into that line, execute whatever code you want, and then it will return. So all this area is basically checking that on the keyboard. These ones here are checking for the arrow keys and applying the necessary offset, the necessary math to move the cursor in the position that we want based on the key pressed. This one is checking for the key, the space bar, which we are going to use to display, to draw a little circle. And if we press it again, it will remove that circle from there. And the 81 corresponds to the letter Q. So what it's going to do is just quit the program. You see, if it's equal to 81, end the program. And the command ends, just exit. The interpreter stops the program in that point. The reason I'm putting this so far away in the lines starting at 1000 is because usually GoSub calls are very far away in the program, because you don't know when you are designing one of these programs, when you don't know exactly how many lines it's going to take, especially because you're jumping from 10 to 10, then you might add one there, maybe you make a mistake, you debug something, you add another one. So the thing is that you don't want to end up in a point where you run out of line numbers, and then so you want to put it as far away as possible. So I knew that this program in particular would not take more than 100, almost 200, and all of these could be optimized a lot as well. I'm writing this in this way to make it easier to understand, but it could be also optimized, and so it will take less line numbers. So that's why by putting 1000, I'm safe. I know that I will never reach 1000. So I know that there is a safe area where I can put all the different little subroutines. That's why it goes up. The sub is from subroutine. The little subroutines, the little chunks of code that I want to execute independently. Let's explore now these two lines here, 1000, 1010. What it's doing is just preventing the cursor to move beyond the boundaries of the 1024 and 2023. So what it does is checks if the memory 1024, which is the first position, plus the offset is less than 1024, then return. It continues in this loop here. And if it's more than 2023, then returns here as well and continues in the loop. So it doesn't actually apply any poke value, it doesn't do anything beyond that memory location. So this is very important because the Commodore 64 doesn't have really a protection of the memory. It doesn't have like privileges users. It's not like a modern operating system at all. So you have full control of the computer. It's a very simple machine anyway. Compared to nowadays, it's complex, but compared nowadays, it's very simple. And so you have full control and access to the whole system. So if you type the wrong poke command, then you can crash the operating system or something. Just turn it off and on, and should be fine. I never heard of any way you can damage. I heard about different viruses that you can basically software that can affect the hardware by, for example, I remember in the past when people were using mechanical disks. Nowadays we're using SSD, but you could stress the disk head by making it doing very read or write operations very, very quickly. And in that process, you end up crashing the hard drive. So you have a software, a virus, a particular malware that was able to affect the hardware and destroy it. And maybe there are other techniques for other pieces of hardware and equipment, I don't know. But I mean, as far as I know, there was nothing like that similar for the Commodore 64. I wouldn't say that it couldn't be done. I don't think so, really. But I mean, anyway, you are 99.9% of the time safe. You can perfectly write any code you want and make any mistake and write any poke command you want, and you're not going to eventually damage it at all. Let's analyze this little piece of code here, which is where basically the magic happens. Basically, in the screen, we have, for example, the cursor in this position. We don't know if, for example, let's say maybe here there is a dot, maybe there is not, maybe there is another dot around here, another one here. So before we move from this position to the next one. Because we are not overriding anything. What we are doing actually is moving the cursor means that we replace this memory location. We are overriding this memory location by the value that is 224. That is the character corresponding to the full square, the cursor one. So when we do that, we will erase this value. We need to keep an understanding of which memory locations actually contain a particular value. So if we store all the time the full 1000 bytes of the whole screen and try to keep that array in memory and updated it as we move, that will consume a lot of memory in the Commodore 64. We can't afford something like that. So what we are going to do basically is just store. Before we move, we say, okay, before I move, I want to know I am here and I have to move here. Before I do that, I want to know what is located here. So I'm going to save this value somewhere, and then I move this basically cursor here, which what it does is overrides this memory location completely with the value of the cursor. But we already saved whatever was here. It was either a dot or an empty space. Then the next step, what we do is we remove whatever was here. So it will be empty. The cursor is in this new position. But in this previous position, we have to put here whatever is supposed to be there. Let's say, for example, that we have several dots, one next to the other. And the cursor, for example, is here. So in the next step, the cursor will be here, and we have here the dot, and here the dot, and here's an empty space, right? I'm going to put it as an empty square like this. And, well, this dot here in this step was overwritten. So we need to save that value somewhere. So when we move to the next step, we know that we don't care about this anymore, for example. And this one will have to get back to the dot. Here again, we override that with the character corresponding to the full square. And here we have to save this position and say, okay, in that location there was a dot. If there were none, we have to save, okay, in that location was a space. So basically, what we do is, before we move, check the character. What is there? Whenever it's there, I'm going to save it. And then, after I save it, I move. And after I move, I put in the previous position I was, whatever it was supposed to be there. So when I move to the next one, I do the same process again. I save whatever I will encounter before I move, save it. Move. In the previous position, I put whatever it was and keep saved that value of what I'm in, what was in there. And then I move to the next one. And that is the process that it's doing here. So let's see line by line. So MPV is next pointer value. Basically the value that is next after the pointer. So here we see peak as M plus off. So peak takes the value from the memory location that we are inquiring here. Here is going to be 1024 because that's the value of the variable SM plus the offset that in that moment we are planning to do. In this case, it's going to be decided here based on the arrow keys that we pressed. So we know now here what is the value. Basically, this is the value of the next position, basically the next position that the pointer is going to be. So we get here, for example, if it's a dot or a space or something. The dot, I think, is 81. Yeah, that's why it's indicated there. So we get that value there and say, okay, we store that here. Now, the next one, the line 1030, is saying, okay, now poke is going to write something there. Say like SM, which is 1024, plus X, which is the current position we're in. That is, X is keeping, the value X is keeping where we are right now. And the value of is telling where we will be. So plus X, which is whatever number it is that we are in that moment, put the previous pointer value. So because we are moving forward, so we want to put there the previous value that was stored in the previous movement. So we restore whatever value was there before we moved the cursor initially in that position. Then the next line, 1040, we say poke and we say SM plus off. And here is 1024 plus the offset. This is the same value we are inquiring here for knowing what is the value of the memory location that is after. We are basically just actually physically moving the cursor to that new position. So whenever it is, set the value 2024. So it's going to put that square in that memory location, which is the next one we are moving. When I talk about next, don't think about adding something. It could be actually subtracting something, because it could be one of these, for example, moving the arrow backwards. Then in the next one, 1050, what we do is telling poke, CM, this is the color memory, which is here, 55296 plus off. So we are always moving in synchrony with the cursor. We also move the color, and we are telling to put the value number 1, which is the color white. So we actually make sure that every time the character that we are writing and we are positioning that part of the screen is going to be of the color that we decided. You can change this program, make another key, for example, to decide the color. It could be more interesting. But for the time being, this is just to make it simple, just white. Then finally, in the line 1060, we set X equal to off. What we are doing here is that now that we moved, we know that, okay, this is now our current position. So we update that state and say now our current position is the offset is, the X is the value of the offset. And in the next one, 1070, we say, okay, well, previous pointer value is equal to the next pointer value that we picked up here before we started doing all these operations. So we saved that value before we did all our manipulations here, and then at the end we saved that as the previous one. It's not the next one anymore because we already moved. It's going to be the previous one, and then we return, so meaning that we will get back here to the main loop. Finally, these two lines here are using a new highlighting here in the software. I hope you prefer that. I think it's clearer than what I was doing before. Basically, what they do is that every time we press the space, if the previous pointer value was equal to 32, and this is the space, the empty space on a code on the screen code, then if that's the case, if it was a space, then make the previous pointer value equal to 81, which is a circle, a little dot. And the next one does just the opposite. If the previous value was 81, then put a 32. This is what basically it's doing, is that erasing or drawing a dot based on the circumstances. So if the cursor is located in a place where there was a dot, by pressing spacebar, what it's going to do, okay, remove the dot and leave a space. If it was a space, then I want to draw a dot in there, and it's putting a dot. Don't get confused by this number here, 81 and 81, because 81 in pesky is the letter Q, but 81 in screen codes is the dot. And it's a little bit of could be a little bit confusing, because here what we are trying to do is that when I press the letter Q, well, it quits the program for quit. But in this case here, what we are doing is just to draw a circle. So this is also is a reminder that the screen codes are not the same as the pesky codes. And finally here, why do we have this value to be 32? Okay, when we start the program the first time, we start here at the upper left corner of the screen. So the first time we move from this position to this one. What we want is that when we do that, here there will be a space. So it's gonna be like this. We moved here, and there will be a space in this position here. So the first time we do that, we have to tell what we want in that position when we move for the first time, and it's gonna be an empty space. If we just put PPV as 0, the screen code for 0 is an %. So the first time we moved, there will be an % there. And yeah, that happened when I made the program the first time. I was moving and said, wait, there is an ampersand there, and that's the reason. So that's the reason we have a 32 here as a way to initialize that previous value before we start running the program. As we move in other videos, we will do more stuff, but the concepts that you learn here are basically the same. So we will learn about a new command. So when it happens, I will just directly go and explain about that new command that we need, but we don't need to go through all of these again. So feel free to modify this program. This is located in GitHub. There is a link below of a blog post. I'm trying to make a blog post of every video explaining for this Commodore 64 Sprites and Sound development course.
If you like this video, please give me a thumbs up and consider subscribing. Remember, hit the little bell next to the subscribe button so you can get a notification when I release a new video. Also, if you want to support Retro Circuits, you can become a patron. With a little tip, you can help me a lot in this channel to keep continuing making these videos. And as a patron, you can get some perks like behind the scenes content that is released to Patreon first, and more. Thank you and see you next time.